Hi everyone, and welcome to yet another virtual chemistry lesson in the Swedish Chemistry 1 course, where we are currently talking about thermochemistry. This will be the last thermochemistry video for this course, and in this video I will introduce some more concepts regarding enthalpy, enthalpy diagrams, and I will also introduce then Hess's law. So here we go. Here is a model that I like to use when I think about enthalpy changes. Enthalpy, as you recall, is the energy content within a system. It's different types of energy, but it's sort of like energy reservoir we're thinking about. But we're going to make a simplification and just think about chemical energy and heat energy. That's what we're dealing with at the moment. Then you can imagine that the system's energy, its enthalpy, consists of chemical energy and heat energy. And this heat energy is in constant contact with the surroundings, where we have a flow back and forth dependent on where we have the highest heat energy. And you've also seen so far that enthalpy changes, they can occur during physical changes, phase transitions for example, and temperature changes, but also during chemical reactions and chemical changes. So let's look at how this model can help us think about this. So let's start with exothermic reactions. In exothermic reactions, the energy in the bonds of the products will be lower than the bonds of the reactants. Therefore, the difference in energy between the reactants and products will be released, and that takes the form of heat energy. So the heat energy goes up, but however, this system is in constant contact with its surroundings. So that means that this heat energy will be transferred to the surroundings. Since energy flows from the chemical energy to the heat energy to the surroundings, energy leaves the system, which means that the enthalpy of the system will decrease. So that's a way of thinking about it. If we look at endothermic reactions, then we have to think about that the products, they will have a higher energy content than the reactants. That energy has to come from somewhere. That comes from the heat energy within the system. However, if the heat energy in the system is used up, then the energy has to come from the surroundings, because if the system is cooler than the surroundings, energy will flow from the surroundings into the system. Effectively, we add energy into this system this way, and then the enthalpy of this system will also increase. So that's a way of thinking about this. We're also going to look at phase transitions. Let's think about vaporization. We put, for example, water on a stove, we turn the plates on, and we heat up the water until it starts to boil. So what happens is that we will add energy into the system from the surroundings, and that takes the form of heat energy, which will then increase within the system. The chemical energy is unchanged. Water molecules are water molecules even in boiling water and in vapor and in liquid water. So water molecules will be water molecules in this case. But since we add heat energy into the system, then the total energy content within the system, that is enthalpy, will also increase. So we can think about it like that. If we think about condensation, during a condensation process, well, then we will have surroundings that are cooler than the system, pulling energy out of the system, heat energy. That means that the heat energy will be decreased. If we think about water vapor condensing, it will cool down until that step where it turns into a liquid. The chemical energy is unchanged. The water molecules remain water molecules, but the enthalpy of the system decreases because energy is flowing out of the system in the form of heat energy. So that's a model that I like to use when I think about the route the energy is traveling through a system out to its surroundings or vice versa. Maybe it will help you to think about these concepts. I hope so. Now we're going to look at better better enthalpy diagrams that we have used before, because previously we only talked about enthalpy before the reaction and after the reaction and the difference between there. But we also said that we could calculate the enthalpy change by the enthalpy change associated with the bonds breaking and the enthalpy change associated with bonds forming. So let's look at what happens to the bonds within the enthalpy diagram, and let's make a better enthalpy diagram than the ones we have used so far. So let's start with exothermic reactions. We need, if we're going to draw a diagram, we need axes like this. So we're going to have a y-axis with enthalpy and an x-axis with the reaction progress. On this x-axis, we could also write time, for example, but it's as the reaction progresses. For a chemical reaction, we will have reactants turning into products. And we know that energy has to be broken, which requires energy. That means that we need to add energy into the system, and the enthalpy of the system will then increase. So adding energy here will cause this line here, which is the path we're traveling through the system, or the energy path that the system is traveling, you can say. It will increase, and then once we reach a certain point where all of the bonds are broken, new bonds can be formed that releases energy, and the products are formed. What we look at when we talk about this chemical, when we talk about the enthalpy change of a reaction, is the distance between the reactants and products, like before. But to get there, we need to summarize all of the energy required to break the bonds. So we need to summarize this part of the curve with this negative part, which is then associated with the breaking of or formation of new bonds. So breaking bonds requires energy, forming bonds will release energy. We find the difference in between those, and that corresponds to this distance over here. So that is what we actually calculate when we use the formula here. You could, of course, expand on this. You could talk about enthalpy diagrams with Gibbs free energy and stuff like that, but we're going to keep it simple. We're not going to go into the details of the activation energy, which is the height of this part of the curve, but this is a sort of good basic start for you to start learning. And then you can expand on this as you maybe progress into more complicated chemistry of various kinds. If you're in the PDP, then you will expand on these types of curves when you're in the IB, for example. Let's now look at the same thing for an endothermic reaction. You need a graph, just like the previous one, and we start with the reactants turning into products. Bonds have to be broken, and bonds have to be formed, just like the previous example. In this case, then, the bonds that are the bonds that are broken corresponds to an increase in energy, so we need to go up here, and then new bonds are formed, which also gives off energy. We take the difference between this value and this value to get the delta H, the difference between the reactants and products, and that is what we do in this formula, this equation. If the energy associated with breaking the bonds is greater than the energy released when the new bonds are formed, then we will have products at a higher enthalpy than what we started off with the reactants. So there you have two better enthalpy diagrams that more describes what happens to the chemical bonds during exothermic and endothermic processes. Now we're going to get into the final concept of thermochemistry, Hess's law. It was formulated 1840 by Germain-Henri Hess, excuse my poor French, and he stated that the enthalpy change for a stepwise process is the same as the sum of enthalpy changes of all the steps of that process. Okay, what does this mean? Well, it means that the total enthalpy change is independent of the route that is taken to form a certain product. Okay, what does this mean for us, really? Well, it means that as long as you can puzzle together chemical equations into a new chemical equation, and you have known enthalpy changes for those previous ones, then you can calculate the enthalpy change associated with a chemical reaction that you don't know the enthalpy change of. So we use tabulated values for some other reactions that can be puzzled together into the reaction we want, and then we get the enthalpy change for the reaction we want. Let's look at how this is done. Here you have a reaction where you have nitrogen monoxide reacting with oxygen gas to form nitrogen dioxide. We don't know the enthalpy change for this reaction. However, we have some tabulated values. We have this reaction, and we know the enthalpy change associated with that reaction is minus 182.6 kilojoules. You see that these are not the same. It's a different type of reaction. We also have access to this reaction, where we have the enthalpy change being equal to plus 66.4 kilojoules. So an exothermic and an endothermic process here. So these reactions are not the same as this one, but we can puzzle these together to form this one. I'm going to show you how that's done. We combine them into one reaction formula, and then we summarize their enthalpies. So we're going to take all of the reactants of this and add them at the reactant side. We're going to take the products of this reaction and put them on the product side, like so. And then we can also summarize the enthalpies here. So a positive and a negative value being added together, because we have an exothermic and an endothermic process. The neat thing here is that since we have some of the same things on both sides, we can start to cross out things that occur on both sides of this chemical equation. For example, nitrogen molecules appear on both sides, as well as oxygen molecules. So we can cancel out one of those, and then we can cancel the two here, making it effectively a 1. And now, if we rewrite this, you will have the same reaction formula as we had up here that we wanted. And we've summarized the enthalpies of these two steps, which is then minus 116.2 kilojoules. So by knowing enthalpy changes of other reactions, we can puzzle those together to find the enthalpy change of the reaction we're interested in, which is kind of neat. If we were to follow this in an enthalpy diagram, we would have reactants turning into products, and then that would continue reacting as new reactants into new products. This is one way to reach this molecule that we wanted. This is one path we can take through the system, but the enthalpy change in total will be the same as taking, independent of which path we take, we can also take then this path of the system. So if we can calculate this path, then we know that what the enthalpy change associated with this path will be. Please note that I've added an extra oxygen molecule here that doesn't actually react, but it sort of just follows in to make it a 2 here in this expression. Because otherwise this wouldn't be quite balanced. But it follows here and joins in to form this 2. And then we can go up here to form this product. So independent of the path we take, we can take this path, H1 plus H2, or we can take H3. It will still correspond to the same enthalpy change. And that is why we can sort of puzzle together different types of chemical reactions into the one we're actually interested in. So yeah, so we can summarize enthalpies of two different reactions into a new one. However, I showed you an example of a stepwise process where the products of reaction 1 were the reactants of reaction 2. This is not a requirement. It does not have to be a stepwise process. Rather, we can, as long as we can sort of puzzle together chemical equations with known enthalpy changes, then we can form any reaction we want, and it's enthalpy. And the simplest thing we can do is to use values for enthalpy of formation when various types of compounds are formed via their corresponding elements. So let's see if we can do this. Let us calculate the enthalpy change during the thermite reaction. The thermite reaction we talked about in a previous video. It's a reaction that forms iron And actually, this is kind of interesting because I've written the formula incorrectly. So I'm going to change that real quick. Because the products formed in this reaction is actually liquid iron aluminium oxide. This generates such an amount of heat that the iron that is formed will actually be in its liquid state. So this is definitely a strong exothermic reaction. So we expect a large negative value for enthalpy change here. But if we don't have that, how can we figure that out? Well, we can look at tabulated values for enthalpies of formation, and then we can find this following value for enthalpy of formation of aluminium oxide, which is minus 1675.7 kilojoules per mole. So that means that when 1 mole of this compound is made from its elements, this amount of energy is released. Because it's a negative sign, it goes from the system to the surroundings. If we look at this compound as well, iron oxide, iron 3 oxide, well, when 1 mole of iron 3 oxide is made from its elements, 824.2 kilojoules will be released as well. So let's use this information to solve the question, what is the enthalpy change of the thermite reaction? So what we then do is that we write down the formula for this enthalpy of formation. So it's forming 1 mole of this from its corresponding elements. We will make sure that we have a 1 in front of this. That's the convention. So that will mean that we have 2 aluminium plus a half oxygen molecule. Then we'll get, a 1.5 oxygen molecules. Then we'll get this. If we were to balance this, normally we would have a 4 and a 3 and a 2 here. But this is the convention used. We also write down the other one, forming iron 3 oxide from its corresponding elements. Then we write this formula. And looking up in tabulated values, I have a nice book from the university, which I really like, Chemistry and Molecular Approach, which I often look at values in. I find values in there. So how can we use this to solve the problem? Well, we can puzzle these reactions together to form this reaction. So remember that we want iron 3 oxide on the reactant side. That means we have to flip this entire expression. And if we flip the expression, then we will also have to flip the sign of the energy here. So to go the other way would correspond to adding energy instead to an equal amount. So if we just flip this reaction, we have this, and we know it's the energy for that. Good. Now we can combine these two reaction formulae together. So we take and write up all the reactants before the arrow, so the aluminium, the oxygen molecules, and the iron 3 oxide. We make an arrow, then we take all of the products and write them on the product side. And what do we get? Well, first and foremost, we have oxygen molecules in equal amounts on both sides, so they can be cancelled out. And then we have 2 aluminium plus iron 3 oxide forming aluminium oxide and 2 iron, just like our expression up here. So then we can simply summarize the two energies, the two enthalpy changes of these two expressions. We'll get a expression for the change in enthalpy in our chemical reaction, which is minus 851.5 kilojoules per mole. If we were to draw an enthalpy diagram of this, we would have something like this. And I'm going to write down the reaction side by side, so I don't have to do what we did before, introducing other things, just following through the system. But we have a reaction which has a large negative value in enthalpy. So this is reaction 1. with a large negative value in enthalpy difference. Then we have reaction 2, forming these products as well. This would then correspond to the same as going from the sum of those reactants to form the sum of those products will correspond to that step. Because you can take this reaction plus this reaction, cancel out the oxygens on both sides, and you will end up with this reaction. And the difference is then the difference between these two expressions. I find it easier to drawing them side by side like this. If you want to think about it, you can think about that aluminium and oxygen react together to form this. This just stays along for the ride throughout this reaction as well. And oxygen we have on both sides, so that can be simplified away. But I find it easier to just draw these side by side to illustrate their corresponding enthalpy changes. So, that's how we can use Hess's law to calculate the enthalpy change of a reaction that we don't know the enthalpy change of, but we know other reactions and their enthalpy changes. I hope that you've learned something today and that you found the thermochemistry section of the course very interesting. Thank you for your attention. And that will be the end of this video. Thank you so much.